Well, welcome to Lecture 3 for Chemistry 141. We're going to start off by talking about unit analysis, sometimes also called dimensional analysis. And unit analysis really gives us a nice way of making sure that a calculation that we do makes sense and finishes with units that we expect. And this is always a good indication that a calculation has been done correctly. It also gives us a hint as to how our calculation might be able to be done if we don't have an equation, or if we've forgotten how to do a particular equation. We can use unit analysis to figure out what we need to do in order to get an answer that we want. So as an example, we might look at how much volume does 6 grams of mercury contain. And so we have our mass, and we have a density of 13.6 grams per milliliter. Now notice that we've got our density there at 13.6 grams per milliliter, and anytime we have something that's a value per something else, we can always write it as a conversion factor. And so for density, we can actually write it as 13.6 grams per 1 milliliter, or we can write it as 1 milliliter per 13.6 grams. Now these are actually the exact same value, even though numerically they would come out differently, because that milliliter, that 1 milliliter is equivalent to the 13.6 grams for that material. Those two values are actually equivalent. And as we go through the semester, we'll see how this works to our advantage. So when we have a unit analysis method, or when we want to use unit analysis method, the way we want to do that is just to, first thing we want to do is write down any given values that we have, and then we want to multiply that given value by some conversion factor so that the original, some of the original units cancel out. The units we don't want to show up in our final answer will cancel out, and that we're left with any units that we want to be left with. Now occasionally, after we do that next math, we perform that calculation, we get a value, we may find that we're still not at the units that we want, and in this case we just need to repeat step 2, find another conversion factor that gets us closer to the units that we want. And as an example, you might want to find the number of seconds in 2.2 weeks. Well, we know that we don't have a direct conversion for number of seconds in a week. We can, however, break down this calculation into a series of conversions. So we can convert weeks into days, we can convert days into hours, hours into minutes, and then minutes into seconds. So here we have a series of unit analysis calculations, and we can eventually get to our final answer. So that finishes out Chapter E, our essentials, and now we can get into Chapter 1, which starts in on atoms. And one thing that you'll notice about this textbook is it is something that is called an atoms first textbook. So we learn about atoms first, how they're put together, before we start looking at reactions. So Chapter 1, it makes sense, would be called atoms. So first thing we really want to look at is just matter. What is matter? Well, matter in a single word you can say is stuff. And what is stuff? Well, it's stuff that takes up space and has a mass. And so we have volume and a mass there. Most matter in our everyday life is very easily identifiable. However, there were times where matter was not really easily detected. People didn't really understand the concept of a gas or the concept of air having matter, having mass, and taking up that space. Now, anytime that we're going to take matter and do some sort of transformation to it, whether it's a physical transformation or a chemical transformation, the total mass of that matter that you involved in that transformation can't change. And we call that the conservation of mass. Now, if we look at our substances and how we break down matter, we can break it down in a couple of different ways. So we see that matter can be broken down into pure substances or mixtures For right now, we're just going to look at those pure substances. And pure substances can be broken down either into elements or compounds. Now, if you look at elements there, elements have one type of atom. So, for example, a sample of gold, you would just have gold atoms present in there. And anytime we have an elemental substance, we can give that substance an elemental symbol. And we find those on the periodic table. Another example of a pure substance would be a compound. And here we have two or more atom types in that substance, and we give its composition by a chemical formula. So, for example, water. It's still a pure substance. We can have pure water where we have nothing but water molecules in there. However, it's not elemental because those water molecules are made up of hydrogen and oxygen. Another good example might be sugar. Sugar has carbon, hydrogen, and oxygen, but it is possible still to have pure sugar. So that would be a compound. Now, if we go over to our mixtures, we have two different types of mixtures. We have homogeneous mixtures and heterogeneous mixtures. A homogeneous mixture has the same composition throughout that sample. So we have more than one substance in there. However, those substances are evenly distributed, and it doesn't matter where you take your sample from that homogeneous mixture, you'll find the exact same composition. Heterogeneous, on the other hand, has a different composition throughout sample. So where you take your sample does determine what that composition is going to be. Let's look at kind of a chart of what that might look like, and this kind of shows everything, a little bit of a flow chart. So we look at matter. Is there one type of particle, either molecule or atom? If the answer is yes, then you have a pure substance. Can you separate that pure substance into simpler substances? If the answer is no, then you have an element, something like helium. If the answer is yes, then you have a compound. Water can be separated into hydrogen and oxygen through electrical means, and so we can break water down, and so we have a compound, and here we have water. If we have more than one type of particle in matter, then we have a mixture. Okay, and is that mixture uniform throughout? If the answer is no, then you have a heterogeneous mixture. So water and sand at the beach, that would be a heterogeneous mixture because you can separate those out physically. If it is uniform throughout, then you have a homogeneous mixture. So something like sugar in your hot tea. So there you have the same amount of sugar in that first sip as you do in that last sip. And so as a result, you have a homogeneous mixture. It has the exact same composition of tea and sugar molecules all the way throughout that mixture. So when we're doing science here, I always think this is a bit of a funny place for this to show up in the book, but this is where it is. We look at the scientific method, and because we're doing science, we are going to talk just a little bit about the scientific method. Anytime we're doing science, it always starts with observations. It's usually the first time that we see something that we want to get more information about. These observations eventually lead to hypotheses as a way to explain these observations. Why are you seeing what you're seeing? So you make hypotheses. And then you do experiments to test those hypotheses. Is your hypothesis right or is it wrong? If it's wrong, because your experiment shows something else, then you come up with another hypothesis and you do more experiments. Once you eventually reach a series of positive hypotheses or confirmed hypotheses, now you can start creating a scientific theory. And eventually a theory can become a law if it is proven always to be right. So scientific method is really this constant cycle of observation, testing, and the refining of ideas and hypotheses. And this is just a nice little graphic that you can think of it. And it is constant. It is truly a constant observation. Once we reach a conclusion, we still take that conclusion and continue to observe, test, and refine those concepts. Let's take ourselves back maybe a few hundred years here and start looking at where chemistry really kind of started, modern chemistry started. And this started with Dalton and his theories. And he's really considered the father of modern chemistry based on his ideas. So John Dalton started looking at ideas proposed by Democritus way back during the time of Aristotle. Democritus had some ideas about particles. He felt that there was a smallest possible particle that would have the same properties as larger samples, and if you divided that particle down, you would no longer have the same physical properties. So he called that smallest possible particle atom, or atomos. Aristotle had different ideas, and people tended to follow Aristotle with his idea that matter could be divided down as far as possible and always have the same properties. Of course, at the time they obviously couldn't see atoms or even think about what atoms really were, and so the concept of a particle that small was really difficult to explain. However, Dalton really kind of seized upon that concept and started doing a lot of research and came out with some very important laws of matter through his research. The first was conservation of mass, and conservation of mass states that matter is neither created nor destroyed, and that's actually not true. It is possible to destroy matter. We can turn it into energy through nuclear reactions. However, Dalton had no way of knowing that. So it does hold true for the things that we look at primarily in this class, where we're looking at chemical and physical reactions. And so if we're looking at chemical and physical reactions, then that conservation of mass does in fact hold true. So during a chemical reaction, the total mass in a reaction must in fact be conserved. So however much mass we put into a reaction, that's exactly the same mass that we have to get out. Now initially this was really a very difficult law to prove because there were ways of doing experiments that seemed to prove this concept wrong. Let's look at an example here. Now obviously this has a little bit more modern twist to it with a digital balance, but if you can imagine somebody carrying out this reaction on a set of scales a couple hundred years ago, you could see why they might think that the conservation of mass concept was in fact incorrect. So here we have a couple of tablets, Alka-Seltzer, and we're going to put it into water. We know that Alka-Seltzer fizzes, and when it gets put into water, that fizz is caused by the evolution of CO2 gas in interaction with that water. That CO2 gas is now leaving that system, and we see that our system did in fact lose mass, going from 281.97 to 280.23. Well, people couldn't see the gas, so they didn't really understand that it was escaping. Dalton, however, realized that this may be the case, and what he did on subsequent experiments was to encase this whole thing in a large jar to where the gas was trapped and still on the scale, and was able to show that in fact the mass did remain the same. So here's just another example of what we might see for conservation of mass. Here we have sodium metal. It's a solid. If we have 7.7 grams of that, we have chlorine gas, 11.9 grams of chlorine gas. This is what we call a stoichiometric mixture, where we have the exact amount of each of those elements that we need. We have a total mass of our elements of 19.6 grams. We're going to react those and react them completely into sodium chloride solid. We see that the sodium and the chlorine have actually completely combined here in this nice little crystal here, and we end up with 19.6 grams of sodium chloride. So we started with 19.6 grams of elements, and we finish with 19.6 grams of a compound. So the mass of our reactants equals the mass of our product. So we also have the law of definite proportions that came out of Dalton's research. And what this means is that all samples of a given compound always have the same mass proportion of their elements. What does that mean? It means you can't have water with extra oxygen. I've actually seen that advertised as super water, where you have water that can extra oxygenate your body because it has extra oxygen in there. Well, you can't do that. Water has a physical or a chemical compound of 2 hydrogen atoms and an oxygen atom, and that's water. If it has anything else in there, then it's not water. So law of definite proportions. Basically, a compound always has the exact same ratio of the different elements for every molecule of that compound. Okay, it also means that the chemical formula for that compound will always be the same. Water is always H2O, and again, if you have a different chemical formula, then it's a different compound. we have the law of multiple proportions, and this is a little bit of a strange law here that we don't use very often, but it is something just keep in the back of your brain. And what this says is that if two elements can combine in multiple ways, if 1 gram of element A is combined with element B in those two ways, then the ratio of the masses of element B reacted will be a small whole number. So let's just look at an example. So carbon and oxygen can come together in two different gases. We can have carbon dioxide, CO2, and carbon monoxide, CO. And so if we look at how much oxygen can combine with 1 gram of carbon for CO2, we see that we can combine 2.67 grams of oxygen, and for CO we can combine 1.33 grams of oxygen there. And so we get that ratio of 2.67 to 1.33, and we basically get a 2 to 1 ratio there. You would find a similar type whole number ratio in comparing H2O and H2O2. So from all of Dalton's research, he came up with an atomic theory of really what's going on with atoms. And most of what he did is actually wrong. However, it was really a very good starting point for atomic theory. And so let's just take a look at Dalton's atomic theory. Each element is composed of tiny, indestructible atoms, or particles called atoms. While we know that atoms are not indestructible, we split atoms all the time, anytime we do any kind of nuclear reaction. All atoms of a given element have the same mass and the same properties. Well, they do have the same properties, however, not all atoms of a given element have the same mass, because we have things called isotopes, which we will talk about a little bit later in the chapter. Atoms combine in simple whole number ratios to form compounds. For the most part, that holds true. I can't think of any places where that's not true, but I don't know every single situation to occur there. Atoms of one element can't change into another element, and we know that that is not true because when radioactive elements undergo radioactive decay, they do in fact change into atoms of another element. But there was no way for Dalton to know those things at the time. So again, even though most of these are not completely correct, they really did form a good foundation for modern chemistry. Well, that finishes out Lecture 3. Hopefully everything we did here makes sense. And as always, if you have any questions on anything we covered here, please let us know.